Greetings. So today we're going to talk about the kidney, and we want to talk about the kidney in more detail, and in particular we want to talk about the filtration, that is the generation of the filtrate, or the beginning product of the urine. So we have several things that we need to deal with, and the first of the learning objectives then is to explain the renal clearance, and to relate it to what's called the glomerular filtration rate. And recall that the glomerulus was the first capillary bed, and that we were filtering materials out of that first capillary bed. The second is we want to talk about the glomerular filtration rate, how that actually is regulated. And thirdly, we want to define autoregulation and the two mechanisms that are involved in autoregulation within the kidney. Fourth, we will explain how the renal blood flow and the glomerular filtration rate are regulated. And five, we will define filtration load of a freely filtered substance. So we have a lot of things to discuss, and so let's get started. So as you recall, this is our little diagram of the nephron, where we are showing both the vascular portion of the nephron and the renal tubule. So we have the afferent arteriole, which is feeding into the glomerulus, our first capillary bed, and that is then drained by the efferent arteriole. The efferent arteriole then has blood leaving the efferent arteriole and entering into a second capillary. Within the cortex, this capillary is called peritubular capillary. This particular capillary will run all the way along the tubule. And in the case of the juxtamedullary nephrons, the capillary changes its name to vasa recta, and we'll talk about that when we deal with the function of the vasa recta in a later lecture. But the functions of these secondary capillary beds are the same, whether it's called peritubular capillary or vasa recta. The other thing that's shown here is we have our little blind-ended renal tubule, where we have Bowman's capsule, which is surrounding or making a cap around the glomerulus, and that this is continuous with the renal tubule itself. And we said that in the beginning we will have a filtration event which will allow fluid and ions to move across this barrier, that is the difference between the first capillary epithelial cell and the basal lamina. The basal lamina then of the second structure, which is Bowman's capsule, those epithelial cells themselves, and that the material will then enter into the renal tubule. So that's going to be filtration, and that as the filtrate moves along the tubule, we can have reabsorption or secretion, and eventually we end up with urine. So what is of interest is to know how well the kidney is working. And one of the ways to measure this is to measure its glomerular filtration rate. So if we have a substance where the substance is neither reabsorbed nor secreted, then the filtration rate of that substance is going to be equal to the excretion rate. So that is how quickly that it ends up in the urine. And we can measure both the filtration rate and we can measure its excretion rate, obviously, by taking a urine sample. And we can measure the filtration rate then by using this substance, which is not reabsorbed nor secreted, but is freely filtered. This is called clearance. This is the removal of the substance from plasma. And one of the substances that's ideal for this type of measurement is called inulin. This is inulin. It's not insulin, but inulin. And inulin is a large polysaccharide. It's a polymer of fructose. Inulin is freely filtered. It enters into the tubule, but it's not reabsorbed and it's not secreted, so that its excretion rate equals the filtration rate. And by using inulin, then we can measure GFR, or the glomerular filtration rate. Then if you want to know how quickly some other substance is removed from the body, then you can measure its concentration within the plasma, and you can measure its concentration within urine, and you can take a timed urine sample, so that by using these three parameters we can calculate the clearance or the removal of a substance from plasma. When we do so, we can calculate its clearance rate. We can then compare it to inulin, and if it's equal to inulin, then we know that it was neither reabsorbed nor secreted. But if it's less than inulin, then that implies that it has a net reabsorption of the substance. And if it's greater than inulin, then we have a net secretion of the substance. So what actually governs the filtration to begin with? So we have two parameters that we have to be thinking about. One is the actual structure of the filtration barrier itself, and as I said, that's the cells which are lining the epithelium of the glomerulus. These are actually very leaky capillaries, so they have they're fenestrated capillaries, but that their basal lamina forms a filtration barrier. And then on the other side, we have a fairly leaky epithelium, which are called the podocytes, which are lining the interior Bowman's capsule. So between that, though, we have basal lamina, and this basal lamina forms a filtration barrier which is repelling charged molecules and molecules based on size. So large molecules do not get across this barrier effectively. Cells do not get across this barrier. So all of the blood cells then stay within the blood or within the plasma, the fluid phase of the blood. And all of the large molecules, such as albumin, these large proteins, are going to stay within the blood. But we will allow then water and ions to flow across this filtration barrier. And depending upon the size of the solute and its charge, then they can move across the filtration barrier with more or less ease. The second thing that we have to consider is the actual forces that are moving materials across the barrier. And this is going to involve Starling's forces, which we've already talked about in the cardiovascular system. And as you all know, that across all capillary beds, we have a pressure gradients, which will, if the hydrostatic pressure is greater than the oncotic pressure, then fluid leaves the capillary and enters into the interstitium. And the same thing is occurring here. So the same forces, the hydrostatic forces of the glomerulus, minus the oncotic force of the blood that's within the glomerulus, that's holding the water or moving the water back into the capillary space, are the two forces that we have to deal with. But in addition to those two forces, in this particular structure, we also have to be aware of the hydrostatic pressure that's within the renal tubule. And that's because the renal tubule, unlike the interstitial fluid and interstitium in other parts of the body, the renal tubule is filled with fluid. So there is a pressure within the renal tubule, and that is the hydrostatic pressure of the tubule. And that will oppose, then, filtration. So the filtration pressure, then, is going to be equal to the hydrostatic pressure, which is coming into the glomerulus, minus the oncotic pressure, which is, again, the attraction of water back into the blood, minus the hydrostatic pressure of the fluid, which is sitting within Bowman's capsule. So we have to be aware, then, of the two properties. One is the permeability of the barrier itself to a particular solute, and secondly, the net filtration pressure, which is allowing the material to move across this barrier. Within this particular glomerulus, in a normal kidney, there's always filtration, and there is not reabsorption. Reabsorption, instead, occurs along the peritubular capillary, where the peritubular capillary now has differences in these pressures, and we'll talk about that in the next lecture. But for us to, right now, we want to remember, then, that the net filtration pressure is always going to, in a normal kidney, is such that you will have a filtration event generating the filtrate within this particular region of the tubule. Now, this particular region of the tubule has an afferent arteriole coming into a capillary bed, and it has an efferent arteriole which is draining that particular capillary bed. And that's unlike any other region in the body. And we all know that the arterioles, if we can change the resistance within the arterioles, we can control the pressure which is both downstream of the arteriole and upstream of the arterioles. So that the pressure gradients, then, that are within this system can be altered locally by changing the resistance within these arterioles, both the afferent arteriole and the efferent arteriole. So what are we talking about? So let's remember. So when we were talking about a normal situation, we have an afferent arteriole coming into a capillary. Then that afferent arteriole, as the blood enters, we will have a net filtration into the Bowman's capsule. And that there will be some of the blood which will still bypass this particular region and move into the peritubular capillary, because we will not be removing all of the plasma at this point. So that for each pass, though, that we're taking a subset of plasma, but we're not taking all of the plasma. Otherwise, it'd be like sludge, and you'd never be able to get the red blood cells then through the capillary and into the peritubular capillary. So the viscosity will rise, but we don't want that viscosity to rise that much within the peritubular capillary. Now, if we want to increase the amount of filtration that's going to occur across this glomerulus, we can dilate the afferent arteriole. And by dilating the afferent arteriole, pressure rises within the capillary. And as pressure rises within the capillary, then we have a greater or an increase in GFR. We can do the opposite, and that is increase resistance within that afferent arteriole by simply constricting or decreasing the radius within the afferent arteriole. And by doing that, by contracting the smooth muscles of the afferent arteriole, decreasing the radius of the lumen of that afferent arteriole, resistance rises, and we now will have a decrease in our GFR. So the glomerular filtration then will decrease as we increase resistance within the afferent arteriole. So the afferent arteriole is really critical then for regulating the amount of filtration that's actually going to occur within any given, across any given glomerulus and into the Bowman's capsule. And each one of the nephrons is able to regulate this particular site. But in addition to regulating the afferent arteriole, the efferent arterioles can also be regulated and can be regulated independent of the afferent arteriole. I say, what do I mean by that? And that is that if you think about it, if you increase the sympathetic nervous system, then we can get an increase in vasoconstriction. So we have the alpha adrenergic receptors that are present on the smooth muscle of the afferent arterioles will constrict, and that will increase resistance within the area. And so we can then increase resistance. That will mean that we will decrease flow within the system. We have hormones that can also affect the smooth muscle of both the afferent and the efferent, and one of these hormones is a second vasoconstrictor called antidiuretic hormone, or vasopressin. It works predominantly on the efferent, or more so on the efferent than on the afferent. And so what will happen is that when both of them will have an increase in resistance, the increase in resistance of the efferent arteriole actually counterbalances the loss of pressure coming from by increasing resistance in the afferent, and we sort of compensate to some extent the total filtration pressure within the glomerulus. So it's a complicated system, and so why is it that the body needs to regulate this? I mean, why is the body worrying about doing this? And if you think about it, the kidney is simply filtering the body at all times. So we have 180 liters being filtered per day, and as you start doing different exercises or doing different jobs, using your body for different things, you need to be moving the vasculature from one area to another. That is, the blood delivery goes from one dominant site to another. So, for instance, if we start running a marathon, then the muscles in our legs are demanding more blood flow. And as they're demanding more blood flow, then the blood is being moved into the skeletal muscles and away from other areas of the body, such as the GI tract. But you want the kidney to be working fairly independent of this, and so they want it to be working independent of mean arterial pressure. And the way the kidney works independent of mean arterial pressure is that it changes the resistance within the renal artery, and it changes the resistance within its arterioles. And it's particularly of interest that changing the resistance within these little arterioles which are feeding the filtration units. This is called autoregulation, where the kidney is effectively running independent of mean arterial pressure, and it does so between 80 and 180 millimeters of mercury. So as long as the system, the entire body, is running with a mean arterial pressure between 80 and 180 millimeters of mercury, the kidney adjusts for whatever the blood pressure is that it's getting. And this is simply our equation. Remember, we have delta P over R, where if we change the pressure, that is, we increase pressure within the system, and you increase resistance within the system, you can keep the flow constant within the system. And that's effectively what the kidney is doing. And so this is called autoregulation. The autoregulation is mediated by two major mechanisms. The first is a myogenic mechanism, which, if you all know, that is simply that if we deliver more blood to the arteriole, we will stretch the walls, and as we stretch the smooth muscle of the walls, then that will open stretch-activated channels and allow calcium to enter into those cells, and the smooth muscle cells will contract. And so we get a contraction of the smooth muscle to bring the vessel back to its original diameter, or importantly, the radius. So we can change the resistance. As you change the pressure, you can keep the flow constant through the system. And that's a very local kind of a control. But the kidney also has a second type of control, and that's called the tubular glomerular feedback. And this involves the tubule itself, and the tubule then talks or sends a signal back to the originating glomerulus and controls the flow through the originating glomerulus. And that's what's shown here. Okay, so let's look at our diagram. So we have at the beginning, now we have our afferent arteriole, which is feeding blood into the glomerulus. And then coming from that, we have the efferent arteriole, and that will feed blood into the second capillary. Then within the renal tubule itself, we have flow of filtrate. And as the filtrate is flowing through the renal tubule, that filtrate is sensed, the flow of the filtrate is sensed by a little a set of cells, which are called the macula densa. The macula densa sense not only the flow rate of the filtrate through the system, but that it also can sense the amount of sodium which is being delivered through the system. And the macula densa, if it senses that there's a low flow through the low flow of filtrate through the tubule, it will then set off a little paracrine type of signaling back to the juxtaglomerular cells, which are the smooth muscle cells of the afferent arteriole. So, and these cells are so important that they have their own name. They're called the juxtaglomerular cells, and that is the cells that are sitting right next to this glomerulus. So they're next to the glomerulus. These are the smooth muscle cells of our afferent arteriole. These smooth muscle cells are told to dilate or to relax. The smooth muscle relaxes. The lumen of the vessel dilates. More fluid flows through into the glomerulus. And by having higher pressures within the glomerulus, we increase the filtrate, the pressures within the filtrate. More filtrate is generated, and therefore more filtrate is delivered to our macula densa. So that's a local control of the flow through the system. If conversely, if there is too high of a flow within the system, then the macula densa can also sense this and correct for the flow within the tubules. Now, what's interesting about this system is that those juxtaglomerular cells happen to also be endocrine cells. So when the tubule, the macula densa, senses that there's a low flow rate or low filtrate within the tubule, it interprets that signal as a low blood pressure or low mean arterial pressure within the systemic circulation, and that is within the body itself. And so not only do the macula densa cells cause the juxtaglomerular cells, the smooth muscle cells, to change, to dilate, to relax and to dilate the lumen of the afferent arteriole, but at the same time, those juxtamedullary cells will the juxtaglomerular cells, will secrete the hormone renin. And this renin then will activate, it's an enzyme, and it will activate an entire cascade of factors, and two of which are potent vasoconstrictors. So systemically then, we will increase the concentration of these two potent vasoconstrictors within the system, and they will cause then an increase in resistance within the systemic circulation, and therefore correct for the low mean arterial pressure, which the kidney had interpreted by having a low filtrate flow through the system. And we'll talk some more about this regulation, this feedback loop, this reflex feedback loop, where the kidney is an important regulator then of blood pressure. Now, there are instances where the mean arterial pressure is going to be outside of that boundary of 80 to 180 millimeters of mercury. One instance, of course, is if you start to exercise, you have intense exercise, you can drive up the mean arterial pressure to be greater than 180 millimeters of mercury. This will increase the sympathetic nervous system discharge, and the sympathetic nervous system then will increase resistance throughout the entire vasculature, and by doing that, then it will increase the vascular resistance not only within the other portions of the body, but also in the renal artery, and thereby affect also GFR. So we will have resistance, so the amount of blood being delivered to the kidney will decrease, and we will have a change then in the amount of blood that's going to be filtered by the kidney. So we'll have a drop or a decrease in GFR. In the second instance, we can have a hemorrhage where, let's say you're in a car accident and you cut your leg, and you're losing a lot of blood volume. And say you lose 1 liter to 2 liters of blood volume, and under these conditions then the pressures within the body will fall. Baroreceptors will fire, and when the firing will decrease, and when the firing of the baroreceptors decreases, then we'll have an increase in the sympathetic nervous system discharge, and again this will lead to a decrease in glomerular filtration rate, and instead of having blood going into the kidney, we will then be moving blood then towards the heart and towards the brain. So the body has decided that it needs to take whatever is left within the circulatory system and move it to the two critical organs within the body under these conditions. Now, there's one other concept that we need to talk about, and that's called filtration load. And the filtration load is simply that the plasma concentration of the substance times the glomerular filtration rate. So in a normal kidney, the glomerular filtration rate is 180 liters per day, or 150 milliliters, per minute. So it's 150 milliliters per minute. Sorry, cancel all that thought. It's 125 milliliters per minute, or 180 liters per day. So what are we talking about? So an example would be if we have glucose in our plasma. And the glucose then is at 100 milligrams of glucose in 100 milliliters of blood. And that multiplied by the glomerular filtration rate, or GFR, right, which is 125 milliliters per minute, then would tell us that we have 125 milligrams per minute of glucose, which is being filtered and entering into the filtrate then of the kidney. The interesting thing about glucose is that although we would filter 125 milligrams per minute, glucose is normally completely reabsorbed within the proximal convoluted tubule, and you'll have 0 glucose being excreted from the kidney. Okay, so what are our key concepts then? So the first is this idea of renal clearance, and this is the removal of a substance from the blood. If the substance is freely filtered and not reabsorbed and not secreted, then its clearance is equal to GFR. And inulin is such a substance. Oftentimes, the renal physicians, the nephrologists, will not use inulin per se to measure GFR, but they use creatinine, which is generated from the metabolism of muscle. And in these instances, it gives them an estimate of GFR because the creatinine is slightly secreted. So it's freely filtered by the renal tubule, and it is slightly secreted, so it gives a slightly larger estimate of GFR. The second is that we have the GFR is determined by pressure differences between the glomerulus and Bowman's capsule. So we have Starling's forces, which is the hydrostatic pressure of the capillary, minus the oncotic pressure of the blood itself, minus then the hydrostatic pressure of Bowman's capsule. This is opposing filtration. Third, the GFR, that is the glomerular filtration rate, can be regulated independent of mean arterial pressure between 80 and 100 millimeters of mercury by changing the resistance of the renal arterioles. So these little arterioles which are feeding into that glomerulus, into each nephron, and this is called autoregulation. And the autoregulation has not only the myogenic response, which is just simply stretch-activated channels are involved, that is the transmural pressures that are within the walls of these arterioles, where we can get dilation or constriction in response to changes in pressure in the region, to maintain flow constant. So we have flow equals delta P over R. And also, in this particular instance, we can use the tubular glomerular feedback, and that involves the macula densa and the juxtaglomerular cells, the JG cells, which are the smooth muscle of the afferent arteriole. This is sometimes referred, these two components are referred to as the juxtaglomerular apparatus. And this can be a positive and a negative feedback. So this particular feedback can cause dilation in that region, so it increases pressure within the tubule, but it can also cause constriction so that we can have a decrease in pressure within the tubule. GFR can also be regulated by neural inputs and by endocrine hormones, and so that these reflex loops can feed back and also regulate the smooth muscle of these arterioles. And then lastly, the filtration load of a freely filtered substance is its plasma concentration times GFR. Okay, so the next time that we meet, then we're going to discuss the other functions of the renal tubules in more detail. So we'll see you then.